our video for 5-6, inverse relations and functions. So our essential question here, how can you find the inverse of a function and verify the two functions are inverses? So inverses means basically that you are inverting the domain and the range for whatever function that you have. Sometimes this means actually making the domain into the range and the range into the domain. Sometimes all you're going to be doing is actually switching up your x and your y letters. So all the x's would become y's and all the y's would become x's, and then you would resolve. And you'll see that as we progress through this section. So our first example gives us a table. It says this is a relation. What is the inverse of the relation represented in this table? Well, if you're finding the inverse of something like this, notice it gives you a list of the x's and a list of the y's. So our inverse is going to reverse things. Our inverse, instead of the point -2, 1, we're going to have the point 1, -2. Instead of -1, 4, we're going to have 4, -1. Instead of 0, 3, we're going to have 3, 0. And then 1, 1, when you reverse that, is going to stay 1, 1. So this is the very basic idea behind an inverse. Notice that your x is your independent variable, your y is your dependent variable, and they basically just swap. So the independent becomes dependent and the dependent becomes independent. So your inverse relation, again, it's formed when the independent and dependent variables are reversed. You're swapping the x and the y. And then if an inverse of a function f is a function, then we call that the inverse function. There are times whenever you will take an inverse and what you get for the inverse is not a function. So we would just say that that is the inverse relation rather than an inverse function. So here is example 2, part A. How can you represent the inverse relation of f algebraically? So algebraically, we are going to rewrite this so that we can find the inverse. Anytime you have an f of x, you are going to have to change that to a y. And so then when we do our inverse, we swap the x and the y. So this becomes x equals y squared instead of y equals x squared. And then we resolve for the y. To solve for the y, you're going to take the square root of both sides using the square root property. And remember, whenever we do that property, I would have to put the plus or minus out in front of that equation. So the y is plus or minus x. This is actually not a function because it does not pass the vertical line test. When you have both the positive and the negative square root, it actually looks like a sideways parabola rather than an up and down parabola like the y equals x squared. So part B, it says, how are the graphs of y equals x squared and y equals plus or minus square root of x related? So I'm going to graph these in two different colors. For y equals x squared, again, that's the parent function. We've graphed this a whole lot this year. So there's that. And then in blue, I'm going to graph plus or minus the square root of x. So I'm still going to have 0, 0. I'm going to have 1, 1. 4 would actually go up to positive 2. For the negative version, if I plug in a 1, I'm going to get back negative 1. If I plug in a 4, I'm going to get back negative 2. So it's going to look something like that. And I guess this should not be curling up. That should continue going downward. And you can see here, I don't know if you can see where these two graphs intersect is along the line y equals x. And that's always going to be the case. So anytime you are graphing things to see if they are inverses, they should always reflect over the line y equals x. And that's because of the idea of you swapping the x and y values. So notice in the red function had the 0.42, or I'm sorry, 24. When I take the 0.24 and I reverse it, I get 42, and that's on the blue one. The red one also has the point -24. When I reverse that, I get 4 -2, and that's on the blue one. So you really are just graphing the mapping of reversing all of the x and the y pairs. Now we're going to find the inverse of this function that's given. Again, we are going to change the f of x to a y. And in case it does ask you about like some of the domains and ranges, for f, the domain is 2 to infinity. The range is going to be 0 to infinity. And then once we find our inverse, we're going to look at that domain and range. So, change the f of x to a y. Then to do the inverse, we swap x and y. So I have x equals the square root of y minus 2. I'm going to have to solve this radical equation. So I'm going to square both sides and then add the 2. So I have x squared plus 2 is equal to y. This function, because when you were squaring an x is never going to be able to equal a negative, or I'm sorry, y is never going to be able to equal a negative number. And in fact, y is never going to be able to equal anything that is less than 2, because if I were to graph this, it's never going to go below 2. So this domain is actually going to become the new range, because that's your limitation on what the y values can be in our inverse function. Now you might say, well, I can plug any x value into there, but you do have to consider what the original bound was on x in the function. So because I could not plug, or because I had my range, the y's that I could get back could not be anything other than 0 or greater, that range is actually going to move down here to the domain. And I know it might not seem like that whenever you're looking at the question, because you're like, well, I can plug any of the x's in. But you do need to consider what is going on in the original. So our domains and ranges swap. The domain of f is going to become the range of the inverse, and the range of f is going to become the domain of the inverse. Really, the only time you need to be aware of that is if you do have something like square roots or rationals where you have values that are excluded. If you have cube roots, like what I'm going to be doing here, your domain and range are all real numbers, so when you swap those, you still have all real numbers. So we don't really have to worry about that as much. So I'm going to change that to a y. Then I'm going to swap my x and my y and resolve for the y to get the inverse function. So I am going to move that negative over first. And then cube both sides. When you cube a negative, it's still going to be a negative, so the parentheses really aren't necessary there. And then I'm going to divide both sides by 4. So I get negative 1/4 x cubed is equal to y, and that is going to be my inverse function. And you could always graph that to verify, to make sure that it does map out the way that it's supposed to. Speaking of verifying, we're going to go through another way to verify two functions or inverses of each other, in addition to graphing. So this question says, what is the inverse of f of x is equal to 2x plus 5, and how can you verify this? So let's go ahead and find the inverse first. I'm going to go ahead and swap my x and my y values and then resolve for the y. So I have 1/2 x minus 5/2 is equal to y, whatever I divide by 2. To verify, when two functions are inverses of each other, f of g and g of f have to both equal x. So when you perform the composition of putting the inverse into the original or the original into the inverse, they both have to equal out to just a solitary x. So if we check f of g, so I'm going to call this one g of x just for this example here. That means that I am putting the 1/2 x minus 5/2 into the f function. So that is going to equal 2 times 1/2 x minus 5/2 plus 5. And I want to see what this is going to equal. Well, if I distribute the 2, I get an x minus 5 plus 5. So that simplifies to x. That checks out. When I do g of f, that means I'm putting the 2x plus 5 into the inverse function. So that's half of 2x plus 5 minus 5/2. So if I distribute the half here, I'm going to have x plus 5/2 minus 5/2. The plus and minus add out, and again, I'm left with x. So that's my verification. You can always verify with composition. You can verify through graphing as well. So you can verify, check some different points, but composition is a way to do this algebraically, so you don't actually need to have any graph available. Our next part of this example, because this is part A, is going to build on this. It says, are the two functions x squared plus 5 and the square root of x minus 5 inverses of each other? So again, we could graph, or we can check our f of g. So I'm going to take this and put it in for the variable in f. So I have the square root of x minus 5 squared plus 5, and I want to see if this is equal to x. Well, if I expand this binomial, remember we got to use the rule, the a squared plus 2ab plus b squared. So my a squared is x, my 2ab is going to be minus 10 square root of x, and my b squared is 25. Well, and you can see here, the best I can do is 25 plus 5, which is going to be 30. So this does not check out. When one of them doesn't check out, it's not even necessary to do the other one. But if you did do the other one, it wouldn't work as well. So these are not inverses. They are not inverses because the composition does not equal x. The last thing we're going to look at is a word problem here. We have a sculpture artist is making an ice sculpture of Earth for display. He created a mold that can hold 4.5 liters of ice. So that's going to be the volume of this. The volume is 4.5 liters. It says, what will the radius of the ice sculpture be if he fills the mold all the way? You do have to keep in mind a few connections here, because if we're looking for a radius and we're only given liters, we are going to have to do a conversion. If you recall, 1 liter is equal to 1,000 centimeters cubed, which means 4.5 liters is equal to 4,500 centimeters cubed. And centimeters is something that I can use for my radius. volume of a sphere, because this is, if you're making a sculpture of Earth, you're looking at something that's spherical, is 4/3 pi r cubed. And if I want to find the radius here, it would make more sense to get the radius by itself. I don't actually have to go through and I'm not swapping these variables, but I am kind of isolating the radius here. So first thing I need to do is move the 4/3 over. So that's going to be a reciprocal. So I have 3/4 v is equal to pi r cubed. You have to divide by the pi. Well, when you divide, it's going to go on the bottom of your fraction. The v would really kind of stay on the top of the fraction there. And then you take the cube root of both sides. So r is going to equal the cube root of 3v over 4 pi. We know that volume is 4,500. So this is the cube root of 3 times 4,500 all over 4 pi. This is something you would need to type into a calculator. And when you do that, you get about 10.2 centimeters. This equation here and this equation up here are inverse equations. If I were to take this expression and plug it back in where the r is, I would end up, or if I do that composition, I would end up with I'm not sure that I would end up with a variable. I think I would just end up with maybe not an r because we're plugging in, but I think everything disappears. So they are inverse equations because you're solving one of them for the other. Go back through, check this out. I hope to get some extra videos in Schoology to help you with inverses because it can be a tricky topic and it is something that comes up in trig pre-calc and in calc, so you want to make sure that you do feel relatively confident with this. So go back through, rewatch this video, and reach out to me if you have any questions.